Hello and welcome back, and if you are new here, welcome, we are very glad to have you here. In today's episode we will continue to properly explain everything about biasing NPN transistors, without that total BS, that we have been fed for last 75 plus odd years. It is truly remarkable how every explanation we came across, went out of its way, to insanely complicate this rather simple choice of voltage and current parameters, in order to drive transistor in proper mode of work. Before we begin, a disclaimer. With all seriousness, out of the utmost respect for all our viewers, and especially those who have subscribed to our channel, we would like to clear out one possible point of misconception in this video. We most certainly do not use profanities, we are not being vulgar, and we aim to present to our audience a content that is all ages appropriate and easy to understand, for viewers of all ages and backgrounds. So, let's give definition for abbreviation BS. BS stands for Bovine Sophistry, our preferred interpretation of definitions and explanations by another group, also abbreviated with BS abbreviation, and that is Balderdash Syndicate, most commonly referred to in our videos as electronics intellectual elite, in general. Now, with this little grammar tangent out of the way, let's get back to our business as usual, debunking deliberately complicated simple things in electronics. So, by traditional definition, biasing transistor means applying voltage of 0.7 or more volts, across base emitter junction. Okay, let's bring our NPN transistor on screen, and draw a simple schematic of the definition. The base emitter junction represents points between base and emitter terminals. The definition says, we should apply at least 0.7 volts between these 2 points. Okay, from previous videos, we know that positive terminal of the battery, or power source, goes to the base, and negative to the emitter terminal. So far, simple enough. So, let's bring up a battery of at least 0.7 volts, and connect positive to the base, and negative to the emitter terminal. This is what definition tells us to do. Congratulations! You have just blown your transistor. Let's start counter, how many times we are going to blow up transistor, by just following BS definitions from BS elites. This is 1. Okay, we blew up our first transistor. Maybe problem is not with definition, maybe it's us. The definition tells us 0.7 volts or more. Okay, let's listen to the definition and obey. Let's put 5 volts battery and do everything same again. Congratulations, it's a baby. Congratulations, yes, but not a baby, just another blown up transistor. That's 2. Clearly, the point of biasing is not an increasing voltage for base emitter junction from 0.7 volts up. From our previous video, we have learned that we must never apply voltage across base emitter junction, without base current limiting resistor. By traditional definition, this base current limiting resistor is assumed, but never directly pointed to us as paramount. So, let's introduce a base current limiting resistor RB in the picture. The function of RB resistor is to limit the amount of current flowing into the base terminal. Let's discuss this in details. In first scenario, without RB resistor, the transistor will pull through the base terminal as much current as power source can provide, and it will burn out. This will happen very quickly. From previous video about NPN transistors, we have also learned, by looking up for the parameters in the datasheet, that for this particular transistor 2N3904, the maximum base saturation current is 5 mA. So, in order not to damage our transistor, and safely drive it in saturation mode, we should never exceed 5 mA of base current at any time. So, in order not to blow up our transistor, we must always incorporate base current limiting resistor RB, in our circuit design and implementation, if we want to use transistor as a switch. Of course, paying closer attention to datasheet for this specific transistor, there are two set of parameters for driving this specific transistor into saturation mode. For base current of 1 or 5 mA, we must also provide collector current limiting resistor that will provide 10 or 50 mA of current running into collector terminal, respectively. Only and only, by this combination of base and collector currents, we safely bias the transistor and drive it into saturation mode of work, when it acts like a closed switch in the circuit. Okay, so we see that base and collector currents are predefined by design of the transistor itself. We get those values from the datasheet. But what about voltages? For base emitter junction, we know that by definition, we must provide 0.7 volts or more. And what about collector emitter junction? How much voltage do we apply there? Now, there is a bit of cheating that we can do here. Providing two separate power sources, one for base emitter junction, and the other one for collector emitter junction is unwise. First, it is expensive. Second, it unnecessarily complicates design and implementation of the circuit. So, let's rearrange our circuit design to eliminate both of these two unnecessary complications. We can redraw our circuit to look something like this. Now that we have decided to simplify power supply for our transistor circuit, let's take a look at the datasheet maximum power rating section, and see what is the maximum voltage we can apply over collector emitter junction. The datasheet says 40 volts, but that is the maximum value, under very specific test circumstances. To be on the safe side, we will not exceed more than 30 volts of collector emitter junction, and since we are using one same power source, our base emitter junction will also be 30 volts. Now, we have selected power source, and we have required values for currents. We can now easily calculate value for base current limiting resistor RB, and value for collector current limiting resistor RC. For RC, we use simple Ohm's law, where resistance is proportional to voltage, and inversely proportional to the current. For desired current of 10 mA, we get 3 kilo ohms, and for desired current of 50 mA, we get 600 ohms. For base current, the formula is a little bit different. Here, we have to take into calculation the voltage drop that PN junction between base and emitter terminal imposes on us. We have learned from previous videos that for silicon semiconductors, the value of that voltage drop is 0.7 volts. So, formula goes like this: the resistance for base resistor is proportional to the difference between VCC and voltage drop of 0.7, and inversely proportional to the current. So, we get values of 29.3 and 5.86 kiloohms, respectively. Of course, there is that most important formula, that emitter current is now equal to the sum of base and collector current. Also, we have to point out that selection for RC and RB resistors must take into account the rated power dissipation for selected values of resistance. For collector resistor, rated dissipation power must be at least 0.3 or 1.5 watts, and for base resistor 0.03 or 0.15 watts, respectively. Otherwise, resistor will burn out, because they will not be able to dissipate heat generated by the current flow. This is very important fact to remember and consider when designing and implementing your circuits. Now, logical question is, from where does that 0.7 volts of voltage drop comes from? Let's quickly pull back the block diagram of NPN transistor. You have seen this already in our previous videos. By definition, NPN transistor is one intrinsic semiconductor doped with p-type impurities to form p-type region, sandwiched between two other intrinsic semiconductors, doped with n-type impurities, forming two n-type regions. From previous videos, we also know that when p and n-type regions meet, they form p-n junction. So, in our case the base, which is p-type region, and emitter which is n-type region, together forms one p-n junction. By definition, p-n junction is a rectifying diode. So, all of this can be represented by equivalency scheme of two diodes in series, D1 and D2. Now, please have in mind, that equivalency scheme doesn't mean that these two diodes functions as same as NPN transistor. No, they are just a model, to help us explain voltage drop from previous chapter. Now, also from previous videos, we have learned that, for the diode to start conducting current, you need to overcome internal resistance with which diode pushes back against power source. That internal resistance is defined as voltage drop across the diode. So, in order for the diode to start conducting current, there has to be 0.7 or more volts across diode terminals, anode and cathode. In our case, anode is equivalent to base terminal, and cathode is equivalent to emitter terminal. Since we are not interested in collector-emitter junction, we have grayed it out, as it is not important for this discussion. Again, we must point out, that in real life, two diodes in series like this, do not form NPN transistor. This equivalency is just a simplified explanation of internal voltage drop of base emitter junction in BJT NPN transistors. Now, next thing to explain is biasing transistor for cutoff mode of work. This would be very simple thing to do, if it wasn't for that parasitic base cutoff current, that we talked about in previous videos. Biasing NPN transistor for cutoff mode of work, when it acts like an open switch in the circuit is pretty straightforward. Just make base current 0 and that is it. In practice, this is achieved by disconnecting base terminal from the power source. So, when we apply no voltage, and consequently, no current to the base terminal, we drive transistor in cutoff mode, where no collector, and consequently no emitter current, flows through the circuit. For all practical purposes this is what happens in cutoff mode. On the right hand side we have an equivalency scheme of a circuit with an open switch. Therefore, all of the three currents, collector, base and terminal, are 0 amperes in this mode of work. However, we have learned from previous videos, that there is a fourth current, that manifests itself, when transistor is in cutoff mode of work. That is parasitic base cutoff current. Let's go back, and draw again transistor equivalency scheme with two diodes in series. We have talked about this equivalency scheme a couple of times in our previous videos, and also in this one, so we will just briefly mention, that this two diodes model is used to explain certain behaviors of NPN transistor. By placing two diodes in series like this, you will not get NPN transistor. Function of this model is to help us explain how two PN junctions behave when certain conditions are met. So, we know that, when we apply very high voltage across collector-emitter junction, but not more than 30 volts, diode D2 becomes forward biased, and we can replace her with equivalency resistor RBE. Also, since that resistor has a very small value, in this circumstances it can be disregarded, and entire scheme can be redrawn like this. What we have left now is just diode D1, that is reverse biased. We have learned from previous videos, that when we reverse bias the diode, or plainly said, when we flip the diode other way around in the circuit, there is small, but insignificant current running through the diode. This current is called the base cutoff current, and it is parasitic, or plainly said, undesirable. However, it is there. We can look up for its value in the datasheet, in off characteristics section. So, in real life, even when the transistor is in cutoff mode, there is still a small current present. This current is often disregarded, as its value is in range of nanoamperes, that is in range of 10 to the power of -9. However, it is there, and if that is something that is important in your circuit, you should take this into your calculations. For all other practical purposes, this current is considered non-existing. You see, when explained without any gobbledygook, biasing transistor for switch mode of work is pretty straightforward. Let's give a quick summary, and run down through all important things. Select desired type of NPN transistor. We use ubiquitous 2N3904 NPN transistor. Select suitable power source to power base emitter and collector emitter junction. Power source must be greater than 0.7 volts. Most common voltages are 1.5, 3, 5, 9, 12, 24 and 30 volts. From datasheets off characteristics section, look up values for base and collector current to drive transistor in saturation mode. Use provided formulas to calculate values for resistor at collector and resistor at base terminal. If you want to drive transistor in cutoff mode, disconnect base terminal from power source. Remember that even when you disconnect base from power source and leave collector emitter junction powered, there is still going to be present small parasitic base cutoff current IBL. And most important thing, never power the circuit without suitable base and collector resistors present. Please, before you leave, show your appreciation by liking this video, sharing it, leaving a comment, and consider subscribing. Thank you, and see you next time. Bye.